Now, the second assumption, or the second feature that a system needs in order to be linear, and in order for us to disentangle the response to multiple contiguous trials, is superposition. Now, what we mean by superposition is simply the fact that if you know the response to one trial and the response to a second trial, if they occur nearby, then you can add the two, and you can actually get the response to overlapping trials. Right. So in other words, if you know the response to a single trial, you can just add them up and get this sort of overlapping trial. Now, is this true of bulk data? Well, Dale and Buckner actually looked into this some years ago now, and they used a very clever experimental design, and it went as follows. Some trials were so-called one trial. So this would be, you would have a single trial of a few seconds, or maybe in fact 1 second, if I remember correctly, in which they would show a stimulus such as this one. So a flickering checkerboard for just about 1 second. And then there would be a long interval before they would show it again. So before there would be a second trial. Then they would have so-called two trial events. And here they would show one trial, then a little break, and then another trial, so that the bold response would overlap between the two. And then finally, they also had three trial events. Same thing, but now you would have it 3 times. So stimulus on, stimulus off, stimulus on, stimulus off, stimulus on, stimulus off. And of course, also in this case, the bold response to each stimulus is overlapping with the beginning of the next trial. So the cumulative response is overlapping. And so their question, so for example, you can see here, maybe this is the stimulation. So here's the response to a one stimulus trial. And you can see, as usual, it takes maybe 6 to 8 seconds for the response to peak, and then a total of maybe up to 12 seconds for the response to come down to baseline. Now, what happens if instead of waiting 12 seconds, you hit the participant again with a second stimulus after 5 seconds? So the response is peaking, is coming here, and then right at this time, what happens if you hit them again with a second stimulus? Well, what you get is that sort of double mountain that we saw earlier. And now, of course, remember, we are left with trying to understand, well, how much of this double mountain is due to trial number 1, maybe this much, and how much is due to trial number 2. And so they thought, well, given this design, we could take the response to 2, right here, subtract from it the response to 1, and we should be left, if the system has superposition, we should be left with exactly an identical copy of the response to 1. And in fact, this is what they see. Here's the response to 1, right, the one that they subtracted out. What they're left with, so the estimated response to the second trial, is actually a little bit smaller than the response to 1, so they're not identical. So when you have 2 trials back to back, the estimated second trial is actually a little smaller than the first trial. It doesn't look like the second trial is an identical copy of the first one. It somehow has shrunk a little bit. In fact, you can keep playing this game, and you can take the response to 3 trials, which is this giant mountain right here, subtract from it the response to 2 trial, which is the middle mountain, subtract from that the response to the 1 trial, and if the system had perfect superposition, we should be able to subtract from the 3 the 2, and from the 2 the 1, and have 3 identical copies of the same response to 1 stimulus. Turns out that's not the case. The one with the little circles is the observed response to just 1 trial. The other 2, the one with the diamonds, is the response to the second trial, the inferred response to the second trial. And the number 3, which you're seeing here in the squares, is the inferred response to the third trial. And as you can see, they are different. So this means that when you have contiguous trials, It's not that you just keep getting the same magnitude of response to the first as to the second as to the third. The magnitude of the response changes a little bit when you have back-to-back overlapping stimuli. Here's another example of a similar idea. So what I'm showing here is two stimuli, is the response, the bold response to two different conditions. One is the black line, which will never change, and that's the response to if you have a single stimulus spaced enough from the next stimulus so that the response comes back to baseline. So in other words, that will be the response to a slow event-related design. The full response is shown in black. The red line is the response to a stimulus if it comes a certain number of seconds after a first stimulus. So in this case, the red response is what you get if you wait 8 seconds in between two contiguous trials. And as you can see, if you wait 8 seconds, the second trial is almost identical to the first one. Of course, if you wait 8 seconds in between trials, the first trial has had time to come back down to baseline almost entirely before you hit it again with the second trial. But now let's put those two trials a little closer. Let's put them only 6 seconds away. And now you can see that the response to the single trial is still nice and big. That never changes. But the response to the second trial that comes only 6 seconds after a first trial is now a little smaller. In other words, it's overlapping a little more with the first trial. And now let's put them even closer. Let's put them 4 seconds apart. And you can see that the response to the second stimulus is smaller than the full response to a single stimulus. And the closer you put them, the more the second response shrinks. If you put them only 1 second apart, the response to the second stimulus is only this small. So you can appreciate how there's a trade-off between being able to pack as many trials as possible in as little time as possible, which gives us many more trials, and the more trials, the more power, with the observation that if you put trials too close together, the response you get is actually much smaller. So maybe you're getting more samples of the brain, but overall you're getting a smaller response to the cognitive process of interest. So this is one of the many trade-offs of fMRI, trying to understand just how close, what is the optimal proximity of two trials so that we still get a big response, but we can pack as many stimuli as possible in the same amount of time. And although I haven't seen the most recent data, the general consensus, and this is data-based, particularly Nico Kriegescourt has looked a lot into this, seems to be that around 2 to 4 seconds is a good compromise between the signal getting a little smaller, but being able to put as many trials as possible, particularly if there's some randomization in there. And just to show another example of this idea, this was by Frist and colleagues in 1998. So what they did is they looked at the response to a single word, which is sort of the stimulus that you're seeing here, according to how many words were being played around it. So if you play 10 words per minute, the response to your target word is this much, right? So you get a big response. Now, if you look at the response to a single word in the context of having 15 words per minute, then you still get this nice big response, up and down. Now, if you play more words in that same amount of time, so if you play 30 words per minute, the response to that one single word of interest is now getting smaller. It's about 2/3 of it. See here. If you play 60 words per minute, so at 1 hertz, 1 word a second, the response to your one word of interest is now 1/3 of the original response. And if you play even more, if you play 90 words per minute, you can see that the response is again even smaller. This is just another example showing that it's good to put stimuli nearby each other in this fast event-related design. However, the closer you put them, the smaller the signal you're eliciting is. So again, you have to be able to balance number of trials, and the more the better, with the fact that if you put trials too close nearby, the actual response that you get shrinks. Now, it's also worth noting that this nonlinear response is not the same throughout the brain. Different parts of the brain actually have different nonlinearities. Let me show you what I mean. So these graphs are showing on the x-axis the distance from the caudal-most part of the brain. So it's the distance from the very back of the brain, and it's in millimeters. So the more to the right, the further frontal, the further rostral we are going from the back of the brain. And then you will see two lines. One line is the magnitude, is the magnitude of the bold signal if you leave at least 6 seconds in between stimuli, and that will be the dotted line with the squares. The second line, the dashed line with the triangles, is the magnitude of the response compared the magnitude of the response to if you have intervals of 1 second in between different stimuli, as compared to the magnitude of the response you would get if you had only a single trial. So, for example, if we look at calcarine cortex, which is at the very back of the brain, you would see that if you put trials 6 seconds apart in this line, the magnitude of the response that you get is about 80% of what you would get if you had them 8 to 10 seconds apart. So you're only losing a little bit. You're only losing about 20% of the signal by putting trials 6 seconds apart. If, however, you put trials 1 second apart, the magnitude of the signal that you get, the magnitude of the response to each trial, is between 40 to 50% of what you would get if you had a single trial and then 8 to 10 seconds. But notice what happens as we move further and further away from the back of the brain. The further away we are, the further frontal, the further rostral we are, the greater the nonlinearity. By the time you are 50 millimeters away from the back of the head, if you put trials 1 second apart, you're actually only getting about 10% of the magnitude of the response that you would get if you had individual trials that were at least 8 to 10 seconds away from each other. So different parts of the brain do have different amounts of nonlinearity.